Picture the night sky for a moment, not just as a blanket of twinkling lights, but as a doorway waiting to be pushed open by the most daring missions humanity has ever conceived. Right now, scattered across labs and launch sites around the globe, teams of scientists and engineers are preparing spacecraft that could rewrite the textbooks of science, redefine our place in the universe, and yes, even reshape life here on Earth. This isn't just exploration for the sake of discovery. It's a leap into an era where the impossible becomes routine, where the mysteries we've wondered about for centuries might finally be cracked wide open. We're standing at the edge of something extraordinary. Think about it, within our lifetime, we could witness the first definitive proof of life beyond Earth, the first mining operations on asteroids, or even the first human footsteps on Mars. These aren't scenes ripped from science fiction anymore. They're the real, tangible goals of 25 space missions currently in motion, missions so ambitious, so groundbreaking, that they could alter the trajectory of our species. From unraveling the secrets of dark matter to building the first interstellar probes, each one of these ventures carries the potential to change everything we know. So what makes this moment different? Why now? Because after decades of incremental progress, the pieces are finally falling into place. New technologies are slashing the cost of reaching orbit, international collaborations are pooling knowledge like never before, and a renewed sense of urgency sparked by climate threats and the simple human itch to explore is pushing us further and faster than we've ever gone. This video is your front row ticket to that revolution. We're about to dive into missions that could answer age-old questions, create industries that don't yet exist, and maybe, just maybe, give us a glimpse of our future among the stars. Strap in, because the next chapter of space exploration is already being written, and you won't want to miss a single page. Let's start with the James Webb Space Telescope, a marvel of engineering that's essentially rewiring our understanding of the cosmos. Unlike its predecessor, Hubble, which mostly observed invisible and ultraviolet light, Webb operates in the infrared spectrum, a game changer for astronomy. Why does that matter? Because infrared light pierces through cosmic dust like a beam through fog, revealing hidden stellar nurseries, ancient galaxies, and the faint glow of objects too cold or distant for Hubble to spot. Already, Webb has shattered records, spotting galaxies so old they existed when the universe was just a toddler, barely 300 million years old. These glimpses into the past aren't just about setting cosmic records, they're forcing scientists to rethink how galaxies formed in the first place. Some of these early galaxies are bigger and more mature than our models predicted, as if the universe figured out how to build skyscrapers before we thought it had the tools. But Webb's revelations don't stop there. Its razor-sharp infrared eyes are also dissecting the atmospheres of distant exoplanets, sniffing out chemicals like water vapor, methane, and even potential biosignatures, molecules that could hint at alien life. Imagine analyzing the air of a world light years away and spotting something that looks suspiciously like the fingerprints of biology. That's not sci-fi anymore. Webb's already done it for planets like K218b, where it detected a molecule called dimethyl sulfide, a compound on Earth produced only by living organisms. Could it be a false alarm? Absolutely. But that's the thrill. We're finally playing detective in places where life might exist. Then there's dark matter, the universe's most frustrating mystery. Webb's observations of galaxy collisions and gravitational lensing are providing new clues about how this invisible stuff shapes the cosmos. By mapping the warping of space-time around ancient galaxies, scientists hope to pin down what dark matter actually is, a question that's haunted physics for decades. This telescope isn't just a tool, it's a time machine, a chemical lab, and a cosmic census taker rolled into one. Every image it beams back isn't just data, it's a piece of a puzzle we didn't even know we were missing. And the craziest part, we're only seeing the beginning of what it can do. While the James Webb Space Telescope has already stunned us with its snapshots of ancient galaxies and tantalizing hints of alien atmospheres, some of its most revolutionary work lies in missions that don't always grab headlines, the kind of science that could quietly upend our entire understanding of the cosmos. Take supermassive black holes, for instance. These monstrous gravitational traps, millions or even billions of times heavier than our Sun, lurk at the centers of galaxies. But here's the puzzle. Some of them existed when the universe was shockingly young, too young for current theories to explain how they grew so big so fast. Webb is now hunting these cosmic anomalies in the infrared, searching for quasars, the blazing beacons of light emitted by feeding black holes in the very early universe. If Webb spots enough of them, scientists might finally crack the code of how these giants formed. Did they grow from the collapse of supermassive stars, or were they born from direct collapses of vast gas clouds? The answer could rewrite the first chapters of our cosmic history books, revealing a universe far stranger and more dynamic than we ever imagined. Then there's the chemistry of the cosmos. Webb isn't just looking for life, it's mapping the raw ingredients of planets across the galaxy. By analyzing the light filtering through the atmospheres of distant worlds, it can detect molecules like carbon dioxide, ammonia, or even complex organics. But the real magic happens when it peers at protoplanetary disks, those swirling rings of gas and dust around young stars where planets are born. Here, Webb can spot water, ice, silicates, and hydrocarbons, tracing the recipes that eventually build everything from rocky Earths to gas giants. And it's not just about planets. Webb's infrared vision lets it spy on the icy building blocks of comets and asteroids in our own solar system, uncovering clues about how water and organic molecules, the stuff of life, might have hitchhiked to Earth billions of years ago. That means every time Webb gazes at a distant star's dusty cradle, it's also peering into our own past, piecing together how a barren rock became a living world. But perhaps Webb's most mind-bending mission is probing the era of reionization, a chaotic time a few 100 million years after the Big Bang, when the first stars and galaxies flooded the universe with light, tearing apart the fog of hydrogen gas that filled space. Webb's images of this cosmic dawn could reveal how those pioneer stars, hot, massive, and short-lived, cooked the heavy elements that later formed planets and life. It's like finding the fingerprints of the universe's first architects. Every one of these investigations has the potential to send scientists back to the drawing board. Whether it's black holes defying the laws of growth, planets forming in chemical environments we've never seen, or the faint glow of the universe's first light, Webb isn't just answering questions, it's showing us how much we didn't even know to ask. While the James Webb Space Telescope peers into the universe's deepest secrets, a different kind of mission is unfolding much closer to home, one that's about to put boots back on the moon for the first time in over 50 years. NASA's Artemis program isn't just a nostalgic return to lunar dust. It's a bold, high-stakes blueprint for humanity's future as a multi-planet species. Forget flags and footprints this time. We're building a highway to the stars, starting with a sustainable outpost on the moon that could become the proving ground for everything from Mars missions to a bustling off-world economy. The centerpiece of Artemis, the Lunar Gateway, a cutting-edge space station that will orbit the moon like a cosmic pit stop. Unlike the International Space Station, which circles Earth, the Gateway is designed as a springboard for deeper space exploration. Astronauts will use it as a base camp, descending to the lunar surface in reusable landers and returning to the Gateway with samples or equipment. Think of it as a celestial gas station, a place to refuel, regroup, and push further into the solar system. But here's the twist: the Gateway won't just serve NASA. International partners and private companies will have a stake, turning it into a collaborative hub where lunar tourism, mining, and even manufacturing could one day take root. Down on the surface, Artemis aims to break the cycle of visit and leave that defined the Apollo era. This time, the goal is permanence. NASA plans to establish sustainable habitats near the Moon's south pole, where frozen water hides in permanently shadowed craters. That water is the linchpin of everything drinkable, breathable when split into oxygen, and most importantly, convertible into rocket fuel. Imagine a future where lunar ice is mined, processed, and turned into hydrogen and oxygen to power ships headed to Mars. Suddenly, the Moon isn't just a destination, it's a gas station for the solar system, slashing the cost and complexity of deep space travel, and the ripple effects go even further. Artemis could ignite a lunar economy unlike anything we've seen. Private companies are already chomping at the bit to launch payloads, from scientific instruments to rovers scouting for resources. Some envision lunar regolith, the Moon's dusty soil, being harvested for construction materials, or helium-3 being extracted as a potential fuel for fusion reactors back on Earth. The Moon could become a testing lab for technologies we'll need on Mars, like 3D-printed habitats or closed-loop life support systems that recycle every drop of water and every breath of air. But Artemis isn't just about hardware and economics. It's about rewriting the rules of human exploration. For the first time, the program pledges to land the first woman and first person of color on the Moon, signaling that space isn't just for a select few, it's for everyone. Every moonwalk, every experiment, every screw turned in a lunar habitat will teach us something about surviving and thriving in the harshest environments. And with each lesson, Mars inches closer from a dream to a destination. Artemis isn't the end game, it's the first step in a journey that could stretch far beyond our celestial backyard. The Moon is just the beginning. But Artemis isn't just about setting up shop on the Moon, it's about using our lunar foothold as a launch pad for the next giant leap, Mars. The Moon's low gravity and lack of atmosphere make it an ideal testing ground for technologies that will one day sustain human life on the red planet. Picture this: habitats built from 3D-printed lunar regolith, their walls thick enough to shield astronauts from deadly cosmic radiation, a design that could later be replicated in Martian soil. Or life support systems that squeeze every last drop of moisture from recycled air and waste, perfected in the Moon's airless vacuum before being trusted on a years-long Mars mission. Every experiment conducted in Artemis's lunar outposts isn't just science for the Moon's sake. It's a dress rehearsal for survival in a place where mistakes can't be undone. The real game changer, though, is fuel. The Moon's icy deposits aren't just for drinking, they're the missing link in turning space travel from a one-way sprint into a reusable highway. Water split into hydrogen and oxygen becomes rocket propellant, and if we can produce it on the Moon, suddenly every Mars-bound ship doesn't need to haul all its fuel from Earth. Instead, they can refuel at the gateway or a lunar depot, slashing launch costs by as much as 70%. This isn't just theory. Companies like SpaceX and Blue Origin are already designing landers and tankers around this exact idea. The Moon could become the first interplanetary gas station, turning Artemis from an exploration program into the backbone of a bustling space economy. Yet for all its promise, Artemis's timeline has become a lightning rod for debate. NASA's goal to land astronauts by 2026 feels increasingly precarious, with delays piling up due to technical hurdles and funding battles. Critics argue the program is trying to do too much too fast, while supporters counter that waiting only extends our earthbound limbo. Meanwhile, international partnerships add another layer of complexity. The Artemis Accords, signed by over 30 nations, aim to foster collaboration, but with China racing to build its own lunar base with Russia, some worry the Moon could become a new frontier for geopolitical tension rather than unity. But here's the bigger picture: whether Artemis sticks to its schedule or stumbles, it's already shifting how we think about space. This isn't just about planting flags, it's about proving that humanity can live, work, and thrive beyond Earth. Every bolt tightened on the gateway, every ounce of water extracted from lunar ice, and every sunset watched from a dusty habitat brings us closer to a future where the solar system isn't just a destination, it's home. Imagine holding a piece of another world in your hand, not a meteorite that randomly crashed to Earth, but a carefully selected, perfectly preserved sample of Martian soil. That's exactly what NASA and the European Space Agency are trying to pull off with the most ambitious interplanetary treasure hunt ever attempted, Mars Sample Return. The plan sounds simple: send a rover to collect rocks, package them up, and bring them home, but the execution. It's a high-stakes, multi-mission ballet across 34 million miles of space, involving robots, rockets, and a feat of engineering never before attempted. At the heart of this operation is NASA Perseverance rover, already hard at work in Jezero Crater, a dried-up lakebed that once brimmed with water. This isn't just any patch of Mars, it's a fossil hunting ground where layers of ancient sediment could hold the smoking gun for past microbial life. Perseverance isn't just driving around, it's using a drill to core samples, sealing them in ultra-clean titanium tubes, and leaving these cosmic time capsules strewn across the surface like breadcrumbs for a future mission to retrieve. But here's where it gets tricky. Fetching those samples isn't as easy as sending a rover with a grabber arm. NASA and ESA's plan involves a jaw-dropping relay race. First, a lander will touch down near Perseverance's cache, deploying a small fetch rover to scurry around, pick up the tubes, and load them into a basketball-sized capsule. Then a miniature rocket, yes, a rocket launching from another planet, will blast the capsule into Mars orbit, where an ESA-built spacecraft will swoop in, snag it mid-flight, and haul it back to Earth. The hurdles are dizzying. Mars' thin atmosphere makes precision landings hair-raisingly difficult. The fetch rover has to navigate autonomously across unfamiliar terrain, avoiding rocks and slopes that could trap it. And that rocket, it has to work flawlessly on the first try in an environment with no launch pads, no backup teams, and temperatures that would freeze most electronics solid. One misfire, one software glitch, and billions of dollars worth of science could vanish into the Martian dust. So why take the risk? Because these samples could rewrite biology textbooks. On Earth, our planet's restless geology has recycled almost all traces of its earliest life. But Mars, frozen in time for billions of years, might have preserved the very fossils we've lost here. Even a single speck of organic material, a strand of fossilized microbes, a peculiar ratio of carbon isotopes, could answer the question that's haunted us for centuries: are we alone? Labs on Earth have tools no rover could carry, like atom-scale microscopes and chemical analyzers sensitive enough to detect a fingerprint of life too subtle for any machine on Mars. And the implications stretch beyond astrobiology. These samples could reveal how Mars transformed from a wet, warm world into a barren desert, offering clues about climate change on a planetary scale. They might even contain resources, metals, minerals, or water traces that future astronauts could use to survive there. Mars Sample Return isn't just a mission, it's the opening act of a new era. If it succeeds, it proves we can reach out, touch another world, and bring a piece of it home, a skill that could one day apply to asteroids, moons, or even the icy plumes of Enceladus. But first, we have to stick the landing, literally. Bringing Martian soil back to Earth isn't just a technical challenge, it's a planetary safety dilemma. What if those carefully sealed tubes harbor something unexpected? A long-dormant microbe, a trace of ancient biochemistry, or even a substance entirely alien to our understanding of life. The stakes are so high that NASA and ESA have spent years designing a containment protocol worthy of a sci-fi thriller. These samples won't just land in a lab, they'll be quarantined in a facility with multiple layers of physical and biological barriers, scrutinized by scientists in hazmat suits until deemed safe. The goal isn't paranoia, it's planetary protection. Earth's ecosystems have never encountered Martian material, and while the odds of a space plague are astronomically low, the consequences of guessing wrong are too dire to ignore. Yet the risks cut both ways. If we mishandle these samples, we could contaminate them with earthly microbes, ruining any chance of spotting authentic Martian life. Imagine the tragedy. After billions spent and decades of effort, the smoking gun for extraterrestrial biology turns out to be a stubborn Earth bacterium that hitched a ride. That's why every step, from the sterilized drill bits on Perseverance to the hermetically sealed gloves in the receiving lab, is engineered to keep both worlds pristine. It's a dance of ultra-clean protocols, one that balances our hunger for discovery with the humility of not knowing what we might unleash. For astrobiologists, though, the gamble is worth it. Martian rocks could hold clues to life's cosmic blueprint, not just whether it exists elsewhere, but how it begins. On Earth, life's origins are buried under eons of geologic churn and biological noise. But Mars, frozen in time, might preserve chemical fossils from when life first flickered into existence. A single amino acid with a unique molecular twist, a lipid membrane in a configuration never seen before, or a mineral structure that only forms in the presence of biology. Any of these could rewrite our definition of life itself. And the implications ripple beyond academia. If Mars once hosted life, even in microbial form, it suggests the universe is teeming with biology. That knowledge would shift humanity's place in the cosmos, turning us from lonely accidents into part of a vast, interconnected web. Conversely, if Mars is barren despite its watery past, it might mean life's spark is rarer than we thought, a humbling reminder of how fragile our existence really is. This isn't just about science, it's about legacy. The samples we bring back could become the most studied rocks in history, pored over by generations of researchers armed with tools we haven't even invented yet. They might hold answers to questions we haven't thought to ask, and tucked inside those titanium tubes there's another possibility: silence. No fossils, no organics, just dust. But even nothingness is data, because in the search for life, knowing where not to look is just as valuable as knowing where to look next. Beneath Europa's cracked, icy shell lies one of the solar system's most tantalizing secrets: an ocean. Not a frozen puddle or a thin layer of slush, but a vast, globe-spanning sea, holding twice as much liquid water as all of Earth's oceans combined. And NASA Europa Clipper isn't just going to admire this alien ocean from afar, it's engineered to hunt for the ingredients of life in a world where sunlight never reaches. This isn't your typical planetary mission. Unlike rovers that trundle across dusty surfaces or orbiters that map terrain from above, the Clipper is a specialist built to answer one burning question: could Europa's hidden depths harbor life? To crack that mystery, it's packing a toolkit straight out of a sci-fi novel. Its ice-penetrating radar, called Reason, will fire radio waves straight through Europa's frozen crust, mapping the thickness of the ice and hunting for pockets of liquid water closer to the surface, potential oases where life might cling. Meanwhile, a thermal imager will scan for heat signatures of recent eruptions, spotting geysers that might spew Europa's ocean water into space like cosmic champagne corks. But the real showstopper is the mass spectrometer, a device so sensitive it can sniff out molecules in parts per billion. As the Clipper swoops just 25 kilometers above Europa's surface, closer than some commercial jets fly on Earth, it'll gulp up particles from those possible plumes, analyzing them for organic compounds like amino acids or lipids. Even more thrilling, it could detect molecular imbalances, chemical fingerprints hinting at metabolic processes happening in the dark, where no sunlight ever fuels life as we know it. Here's the kicker: Europa's ocean isn't serene. It's likely churned by tidal forces, flexed and heated by Jupiter's relentless gravity. That means hydrothermal vents might dot the seafloor, mirroring the scorching, mineral-rich chimneys on Earth's ocean bottoms where life thrives without a shred of sunlight. If the Clipper finds the right cocktail of salts, minerals, and organics in those plume samples, It won't just suggest Europa could support life, it'll scream that the solar system is dripping with habitable real estate. Yet the mission's genius lies in its restraint. The Clipper won't land or melt through the ice. It's a scout gathering data to design a future mission that might dive into the abyss. Every flyby, every plume snapshot is a stepping stone toward the ultimate goal, sending a submersible into Europa's alien ocean where just maybe something is waiting in the dark. Finding microbial life in Europa's dark, salty ocean wouldn't just be a scientific headline, it would shatter our assumptions about where life can exist. Right now, every biology textbook defines life by one golden rule. It needs sunlight, at least indirectly, to survive, but Europa's ocean, locked under miles of ice, is a perpetual midnight zone. If organisms thrive there, they're playing by rules we've never seen, drawing energy not from photosynthesis but from chemical reactions between rock and water. Picture bacteria-like creatures clustered around hydrothermal vents, munching on sulfur or hydrogen, their entire ecosystem fueled by the slow churn of Europa's tidal heating. That wouldn't just expand the habitable zone, it would explode it, proving life can ignite in places we once wrote off as sterile. And here's the mind-bending part. If life emerged independently on Europa, it might not resemble Earth's biology at all. Our DNA, our cell structures, even the way we store energy, all of it could be just one version of how life assembles itself. Europa's organisms might use different amino acids or a mirror image version of our molecules, like a left-handed glove in a world of right-handed handshakes. That discovery would mean life isn't a fluke tethered to Earth-like conditions. It's a cosmic inevitability, popping up wherever there's liquid water, energy, and time. But the implications run deeper than biology. If Europa hosts life, then why not Enceladus with its own subsurface ocean and geysers, or Ganymede, where an even larger sea sloshes beneath the ice? Suddenly, the solar system becomes a chain of potential oases, each with its own story. And if life can thrive in these frozen, lightless realms, what stops it from existing in the buried oceans of exoplanets light years away? The Drake equation, the formula estimating intelligent civilizations in our galaxy, would need a complete overhaul, with habitable worlds revised from a handful to billions. Yet there's a humbling counterpoint. Europa's life, if it exists, might share a common ancestor with Earth's. Meteorites have swapped material between planets for eons, and its possible microbes hitched a ride on debris from an ancient Martian impact seeding both worlds. If Europa's organisms match ours genetically, it would suggest life spreads like cosmic pollen, but if they're truly alien, it means the universe is a laboratory running infinite experiments. Either way, the discovery would rewrite what it means to be alive. We'd no longer be solitary inhabitants of a pale blue dot, but neighbors in a galaxy teeming with possibilities. And perhaps most profoundly, it would force us to confront a new question. If life is everywhere, why haven't we found the others yet? Swapping Europa's icy ocean for Titan's hazy orange skies, NASA, a Dragonfly mission, will attempt something no spacecraft has ever done: fly like a mechanical mosquito across an alien moon. But this isn't just a joyride, it's a time machine. Titan, Saturn's largest moon, is a frozen snapshot of early Earth, wrapped in a nitrogen-rich atmosphere thicker than our own, with rivers, lakes, and even rain. Only here, the liquid isn't water, it's methane, cascading in slow motion under gravity 1/3 as strong as Earth's. And Dragonfly, a nuclear-powered drone the size of a compact car, will hop between these otherworldly landscapes, hunting for the chemical recipes that might have sparked life billions of years ago. What makes Titan so special? It's the only place in the solar system besides Earth with stable liquid on its surface, but swap water for hydrocarbons and you get a surreal mirror world. Methane evaporates into yellow clouds, condenses into droplets, and fills vast seas like Kraken Mare, a body of liquid larger than the Great Lakes. ethane and propane mix into viscous rivers carving valleys through icy bedrock. And beneath it all, scientists suspect a global ocean of water and ammonia, shielded by an ice shell, meaning Titan might host two potential habitats, one exotic, one familiar. Dragonfly's genius lies in its mobility. Unlike rovers limited by rough terrain, this 8-rotor drone will leapfrog up to 8 kilometers at a time, spending Titan's long days equivalent to 16 Earth days, recharging via a radioactive power source before flying to a new site. Each landing zone is a calculated gamble. Near the equator, it'll explore dunes of organic sand, dark grains of complex carbon molecules that rain from the sky. Farther north, it might skim the shores of methane lakes, sampling sediments where liquid and ice interact. But the real prize is probiotic chemistry, the reactions that turn simple molecules into the building blocks of life. Titan's atmosphere is a factory for these compounds. Sunlight zaps nitrogen and methane, forming compounds like hydrogen cyanide and benzene, which clump into haze particles and snow onto the surface. In labs on Earth, similar molecules, when given energy and time, form amino acids and nucleobases, the stuff of proteins and DNA. Dragonfly's instruments will grind up Titan's soil, vaporize it, and analyze the fumes, hunting for these biological precursors. The parallels to early Earth are uncanny. Billions of years ago, before oxygen filled our skies, our planet might have resembled Titan, a place where carbon-rich chemistry simmered in ponds under a hazy sky. Did life here start in such environments? If Dragonfly spots complex organics on Titan, it could mean the universe is primed to cook up life anywhere with the right ingredients, whether water or methane is the solvent. Yet Titan's extreme cold, -179 degrees Celsius, adds a twist. Chemical reactions there unfold in slow motion, like a paused video of Earth's origins. That's why Dragonfly's mission stretches years, to watch how Titan's organic soup evolves season by season, and lurking in the data might be an even wilder possibility. What if Titan's chemistry has already crossed the threshold into something we'd recognize as life? Just not as we know it. Microbes that breathe hydrogen instead of oxygen, or cells with membranes built from acrylonitrile, a molecule detected in Titan's atmosphere. Dragonfly isn't just exploring another world, it's testing whether life's blueprints are universal, or if we've been missing a whole other chapter in biology's playbook. Every rotor spin, every soil analysis brings us closer to answering whether we're alone, or if the cosmos is far stranger and far richer than we ever imagined. Titan's methane rain falls in slow motion, each droplet nearly twice as large as Earth's, but falling 6 times slower, like syrup dripping through air. Yet this alien weather carves river valleys and smooths pebbles into rounded shapes, mirroring Earth's water-driven geology with eerie precision. Even Titan's dunes, sculpted by winds 10 times weaker than ours, stretch for miles in patterns nearly identical to Namibia's sand seas. The similarities don't stop there. Titan's methane cycle, evaporation, cloud formation, and rainfall replicates Earth's water cycle so closely that scientists call it hydrology's weird twin. But swap water for hydrocarbons, and suddenly a familiar process becomes a window into nature's adaptability. What makes Titan's chemistry so electrifying is how it reroutes life's recipe book. On Earth, water's versatility as a solvent makes it life's indispensable ingredient. But Titan's frigid temperatures turn water to rock-hard ice, leaving methane and ethane as the only liquids capable of mixing molecules. In this freezer-like environment, chemical reactions crawl at a glacial pace, yet lab experiments show that Titan's organic haze particles, when dunked in liquid methane, can form structures eerily reminiscent of cell membranes. These aren't cells as we know them, but they hint at a startling possibility. Life might not need water at all. Instead, it could rely on hydrocarbons as its bloodstream, with energy harvested not from sunlight but from acetylene raining from the sky or hydrogen seeping up from below. The stakes of this discovery are cosmic. If life can thrive in Titan's methane lakes, it means the universe's habitable zones just expanded exponentially, no longer limited to Goldilocks planets with liquid water, but stretching to icy moons and even rogue planets adrift between stars. Titan's chemistry also forces us to rethink life's signatures. On watery worlds, we hunt for oxygen or chlorophyll. On Titan, biosignatures might be vanishingly subtle, a slight imbalance in hydrogen consumption here, an unexpected concentration of complex hydrocarbons there. Dragonfly's sensors are tuned to these nuances, sniffing for anomalies that could betray the presence of something unusual. Yet Titan's greatest lesson might be about patience. On Earth, life exploded in diversity within 1 billion years. Titan's cold slows everything: chemical reactions, geological change, even the pace of evolution. Any life there would operate on timescales we can barely fathom, growing, metabolizing, or reproducing over centuries instead of hours. It's a reminder that the universe doesn't play by Earth's rules, and that the search for life demands we shed our assumptions. Whether Titan hosts biology or not, this hazy moon is already rewriting the playbook for where and how we should look for our cosmic neighbors, perched high in Chile's Atacama Desert, the Vera C. Rubin Observatory isn't just another telescope, it's a cosmic alarm system, a time-lapse camera for the universe, and a dark energy detective all rolled into one. With a lens wider than a giraffe is tall and a resolution that could spot a golf ball from 15 miles away, this ground-based behemoth will perform a feat no observatory has ever managed, mapping the entire visible sky every 3 nights, night after night for a decade. That's like rewriting the celestial atlas in real time, catching everything from killer asteroids to exploding stars before they fade from view. The scale of this operation is staggering. Rubin's camera packs 3.2 billion pixels, so powerful it would take 1,500 high-definition TVs just to display one of its full-resolution images. Each snapshot will capture millions of galaxies, stars, and solar system objects, comparing them to previous scans to flag anything that moves, flickers, or wasn't there before. But here's where it gets urgent. Rubin's relentless gaze could pinpoint up to 90% of near-Earth asteroids large enough to level a city, giving us years, maybe decades, of warning to deflect a potential impact. That's planetary defense shifted from reactive to proactive, turning apocalyptic scenarios into solvable math problems. Yet the real magic lies in Rubin's secondary mission, hunting the universe's biggest enigma, dark energy. This mysterious force, making up 68% of the cosmos, is accelerating the expansion of space itself. Rubin will measure this expansion by mapping billions of galaxies, tracking how their light stretches as space stretches, a galactic ruler that could reveal whether dark energy's strength changes over time. The implications are existential. If dark energy grows stronger, the universe might end in a big rip, tearing atoms apart. If it weakens, gravity could reverse expansion, collapsing everything in a big crunch. Rubin's data might hand us the answer, but dark energy isn't the only shadowy target. Rubin will also chase dark matter, that invisible scaffolding holding galaxies together. By watching how light bends around unseen mass, a phenomenon called gravitational lensing, it could map dark matter's distribution in unprecedented detail. Think of it as an X-ray for the cosmos, revealing the hidden bones beneath the universe's visible flesh. Every night, Rubin will drown astronomers in a fire hose of data, 20 terabytes, equivalent to streaming 4,000 hours of HD video. Machine learning will sift through this deluge, flagging anomalies like supernova, neutron star collisions, or interstellar visitors like Oumuamua. Somewhere in that torrent of pixels might lurk discoveries we haven't even dreamed of yet, a 9th planet hiding in our solar system's outskirts, or a quirk in gravity's laws that upends Einstein. Rubin isn't just a tool, it's a paradigm shift. For the first time, we'll watch the universe as a dynamic, evolving entity, not a static backdrop. The sky won't be the same twice, and neither will our understanding of it. Rubin Observatory's relentless sky scans won't just catalogue cosmic objects, they'll crack open one of the most perplexing riddles in modern physics: why the universe is flying apart faster and faster. This acceleration, discovered in the late 1990s when astronomers spotted distant supernova brighter than they should be, defies everything we thought we knew about gravity. Einstein's equations suggested the cosmos should either expand at a steady pace or slow down as matter's pull acts like a cosmic brake. Instead, something invisible is pressing the gas pedal harder with time. We call this phantom force dark energy, but naming it doesn't explain it. Here's where Rubin's precision becomes revolutionary. By mapping the positions and shapes of billions of galaxies across cosmic time, like a time lapse of the universe's growth, its data will reveal how dark energy's push has changed over billions of years. One leading theory suggests dark energy is the cosmological constant, an unchanging force woven into space itself. But if Rubin detects that galaxies clump differently at various epochs, it could mean dark energy evolves, growing stronger or weaker. That would upend current models, pointing toward undiscovered physics, perhaps extra dimensions or a fifth fundamental force. The observatory's secret weapon is weak gravitational lensing, the subtle warping of light from distant galaxies as it passes massive cosmic structures. By measuring these distortions in Rubin's ultra-deep images, scientists can reconstruct 3D maps of dark matter, which forms an invisible scaffold guiding where galaxies form. Since dark energy counteracts dark matter's gravity, tracing how this scaffold stretches over time acts like a speedometer for the universe's expansion. Unexpected kinks in that timeline might reveal dark energy isn't a constant at all, but a dynamic field with its own rules, a possibility that would send theorists scrambling back to their chalkboards. Even more tantalizing is the chance Rubin could spot anomalies Einstein never predicted. If certain galaxy clusters appear too young or too massive for their cosmic era, it might hint that gravity itself behaves differently on vast scales. Some alternative theories, like modified Newtonian dynamics or emergent gravity, propose that what we call dark energy is just gravity's rules changing in ways we don't yet understand. Rubin's mountain of data will test these radical ideas against cold, hard statistics, either burying them or forcing a rewrite of astrophysics textbooks. Yet the biggest revelation might be sheer cosmic humility. Right now, we're like ants trying to deduce the shape of a forest by studying a single leaf. Rubin's decade-long survey will hand us the entire tree, and with it, the first real shot at understanding whether dark energy is the universe's default setting or a phase in some grander cycle we've yet to imagine. The answers won't just satisfy curiosity, they'll dictate the ultimate fate of everything. A stronger dark energy could tear atoms apart in a big rip. A fading one might let gravity claw back, collapsing the cosmos into a fiery crunch. Or maybe, just maybe, we'll find the universe has surprises no model predicted. Imagine a telescope so powerful it could spot a city on Pluto, or zoom in on an Earth-sized world orbiting another star and analyze the colors of its sunset. That's LUVOIR NAS, a most ambitious dream for a next-generation space observatory. While Hubble showed us the cosmos in stunning detail and Webb peered through cosmic dust to the universe's infancy, LUVOIR is designed to do something even more profound: hunt for life itself by studying planets so alien yet so familiar they could be mirror versions of our own. This isn't just an upgrade, it's a quantum leap. LUVOIR primary mirror could span up to 15 meters, dwarfing Webb's 6.5 meters and Hubble's modest 2.4. That colossal light-gathering power, combined with cutting-edge coronagraphs to block out stellar glare, means it wouldn't just detect exoplanets as faint blips. It would photograph them in rich color, mapping continents, clouds, and even seasonal changes on worlds dozens of light years away. Picture an alien Earth glowing blue in the darkness, its atmosphere streaked with weather patterns, its surface reflecting hints of oceans or forests. That's the level of detail LUVOIR promises, but the real magic lies in its spectral vision. By dissecting the light filtering through these exoplanet atmospheres, LUVOIR could sniff out molecular fingerprints like oxygen, methane, or even chlorophyll, chemicals that don't last long unless replenished by life. On Earth, oxygen is a product of photosynthesis. Finding it elsewhere, especially paired with methane, which oxygen normally destroys, would be a siren call for biology. The telescope's ultraviolet eyes could also spot ozone, a shield against deadly radiation, while its infrared sensors might catch the heat signature of cities or industrial activity. Yes, we're talking about hunting for technosignatures, evidence that we're not the only civilization to tame fire and invent the light bulb. LUVOIR targets aren't just hypothetical. Scientists have already catalogued potentially habitable worlds like Proxima Centauri b and the TRAPPIST-1 system, rocky planets bathing in the gentle warmth of their stars. But current telescopes can't tell us if their skies are thick with nitrogen like ours or poisoned by volcanic sulfur. LUVOIR would change that, ranking these worlds by their potential to host life and answering whether pale blue dots are cosmic rarities or as common as sand on a beach. Building this behemoth won't be easy. Its segmented mirror would need near-perfect alignment in space, and the coronagraph technology to block starlight is still being tested. Then there's the price tag, an estimated $11 billion, more than Webb's famously bloated budget. But the payoff, a telescope that doesn't just push boundaries but redraws them. LUVOIR could settle the Fermi paradox by proving life teems across the galaxy, or deliver the haunting realization that Earth is a solitary oasis in a sterile universe. Either way, it would redefine our place in the cosmos, not just as observers but as participants in a story far bigger than ourselves. And here's the kicker, LUVOIR isn't just about finding life. It's about time travel. By studying young stars and their protoplanetary disks, it could watch solar systems like ours being born, revealing how often Earth-like worlds emerge. It might spot icy moons around distant gas giants, hinting at another Europa or Enceladus hiding in the dark. Every image it captures would be a frame in the universe's greatest home movie, showing how planets and perhaps life grow from stardust. The telescope's proposed launch in the 2030s feels agonizingly far off, but the science it would unleash is timeless. LUVOIR isn't just a tool, it's a mirror held up to the cosmos, reflecting back not just light but answers to questions we've asked since we first looked up at the stars. Are we alone? Are there others like us? Or is Earth's flicker of life the universe's most extraordinary accident? For the first time in history, we're building a machine that could silence the speculation with a single, breathtaking image, another world alive under an alien sun. The moment LUVOIR captures undeniable proof of life beyond Earth, the shockwaves won't just ripple through laboratories, they'll tear through the very foundations of human belief. Organized religions, many built on the idea that humanity holds a special place in creation, would face profound existential questions. Would the discovery of microbial life on a distant exoplanet challenge Scripture, or could faiths adapt by interpreting their teachings as universal truths encompassing all life? Some theologians argue that finding extraterrestrial biology would enrich spirituality, painting God as a cosmic artisan rather than a terrestrial sculptor. Others fear it could fracture faith communities, sparking fundamentalist backlash or radical reinterpretations of sacred texts. The Vatican's own astronomers have already weighed in, stating that alien life would glorify the Creator, but not every pulpit would echo that optimism. Philosophers, meanwhile, would grapple with a more unsettling question. What happens to human exceptionalism when we're no longer the universe's only thinkers? For centuries, we've framed consciousness as a rare fluke, a spark lit against improbable odds. Proof that life arises easily elsewhere would force a Copernican-level reckoning, dethroning us from the center of biological importance. Some might find liberation in this cosmic humility, embracing our role as one thread in a vast tapestry of existence. Others could spiral into nihilism, questioning whether meaning persists if life is commonplace. And if LUVOIR detects not just life but intelligence, say atmospheric pollutants hinting at industry, the stakes skyrocket. Are we junior members of a galactic community, or are we the lonely pioneers, light years ahead of other civilizations? The telescope's data might not just answer, are we alone, but do we matter? Yet the greatest upheaval could be geopolitical. History suggests that humanity doesn't handle existential shocks with grace. The Cold War space race proved that competition drives progress, but cooperation is fragile. If LUVOIR spots a habitable world ripe for exploration, would nations unite under a shared mission, or would we export our rivalries to the stars? The Outer Space Treaty of 1967 forbids territorial claims on celestial bodies, but legal frameworks crumble under ambition. A planet teeming with life could become the ultimate prize, triggering a scramble for resources or scientific dominance. Alternatively, contact, even indirect, might dissolve borders overnight, as Earth confronts its identity as a single species adrift in an incomprehensibly vast universe. The irony is palpable. A machine designed to collect photons could end up holding a mirror to humanity's deepest fears and highest aspirations. Whether LUVOIR revelations bring unity or chaos won't depend on the telescope's optics, but on our willingness to see ourselves not as the protagonists of this story, but as participants in something infinitely grander. Imagine this: a fleet of spacecraft no heavier than a paperclip, hurtling through the void at 1/5 the speed of light, fast enough to reach the nearest star in just 20 years instead of millennia. This isn't the plot of a sci-fi novel. It's breakthrough Starshot, the most audacious interstellar mission ever conceived. The target, Alpha Centauri, our stellar next-door neighbor at 4.3 light-years away. The catch: these aren't traditional rockets with roaring engines and bulky fuel tanks. They're nanocraft silicon wafers thinner than a human hair, each carrying cameras, sensors, and a tiny sail thinner than a soap bubble. The propulsion system sounds like something from a futuristic thriller: a 100-gigawatt laser array stationed on Earth, firing a concentrated beam of light at these minuscule sails. As photons strike the sail's reflective surface, they transfer momentum, not with the gentle push of a breeze, but with the force of a hurricane, accelerating the probes to a staggering 60,000 kilometers per second in under 10 minutes. To put that in perspective, at peak speed, these nanocraft could zip from New York to London in less than a heartbeat, but the engineering hurdles are as vast as the distances involved. The sail material must be nearly perfect, free of microscopic flaws that could tear it apart under acceleration, forces thousands of times stronger than Earth's gravity. The laser array, spanning kilometers, needs pinpoint accuracy to keep the beam focused on sails the size of postage stamps as they vanish into the darkness. Even starlight becomes a hazard. A single cosmic ray strike could fry the onboard electronics, which must survive decades of deep space radiation with less shielding than a smartphone case. And then there's the data problem. At Alpha Centauri, the probes won't have the power to slow down. They'll scream past the star system in mere hours. In that blink of time, their tiny cameras must snap high-resolution images of any planets, while a laser transmitter no larger than a grain of rice beams the data back to Earth. Receiving those faint signals across 4 light-years will require a global network of radio telescopes listening for whispers in the static. The payoff: a close-up glimpse of Proxima Centauri b, a rocky world in the habitable zone where temperatures might allow liquid water and just maybe the ingredients for life. Starshot's images could reveal alien coastlines, weather patterns, or even biosignatures in the atmosphere. But even if the system proves barren, the mission would mark a turning point, the moment humanity became an interstellar species, if only by proxy. The timeline is as ambitious as the technology. With funding and breakthroughs, the first launch could happen in the 2030s, reaching Alpha Centauri by mid-century. Along the way, Starshot would revolutionize space travel itself, proving that laser propulsion could slash transit times to Mars or the outer solar system. Some visionaries even dream of scaling up the concept, envisioning future sails large enough to carry human colonists to the stars. Of course, skeptics abound. The laser power required dwarfs all nuclear plants on Earth combined. The cost billions at least makes it a hard sell for governments, and there's no guarantee the fragile probes will survive the journey. But here's the radical truth: Starshot doesn't need all its tiny explorers to succeed. Even one intact craft returning data would shatter records, offering humanity its first postcard from another star. This isn't just about reaching Alpha Centauri, it's about proving that the stars aren't out of reach. For millennia, we've looked up and wondered. Soon, we might finally touch them, not with ships but with light. Starshot's vision of interstellar travel sounds revolutionary until you account for the universe's chaotic obstacle course. Even at 20% light speed, a collision with a speck of dust smaller than a grain of sand could shred the wafer-thin probes, turning billion-dollar dreams into cosmic confetti. In the void between stars, interstellar dust isn't just a nuisance. It's a hailstorm of frozen particles and tiny meteoroids, each packing the kinetic punch of a bullet when struck at relativistic speeds. Engineers have proposed shielding solutions, atom-thin layers of graphene or beryllium copper, but no material yet known could fully deflect a direct hit. The probes might rely on redundancy instead, launching thousands to ensure a few survive the journey, like dandelion seeds braving a storm. Then there's the laser itself. Generating a 100-gigawatt beam, roughly the output of 100 nuclear reactors, requires breakthroughs in photonics we haven't yet achieved. Current lasers lose coherence over distance, their beams scattering like flashlight rays. Starshot's design calls for an array of millions of small lasers synchronized to act as one, a feat comparable to conducting an orchestra of violins spread across a continent. Even a slight misalignment could divert the beam, leaving the probe stranded. And let's not forget Earth's atmosphere, which distorts light like a funhouse mirror. Solutions like floating laser platforms in the stratosphere or lunar-based arrays have been floated, but each adds layers of complexity and cost. Funding is another quagmire. Breakthrough Starshot's initial $100 million commitment from billionaire Yuri Milner is a drop in the bucket next to the projected $10 billion needed to make the mission viable. History isn't kind to privately funded megaprojects. Remember the Solar Clipper, a solar sail concept abandoned after investors balked at escalating costs. Unlike government programs which can absorb delays, private ventures live or die by quarterly reports. Skeptics argue that without NASA or ESA-level backing, Starshot risks becoming another ambitious PowerPoint presentation, like the now-defunct Project Daedalus of the 1970s. Yet the project's defenders counter that private funding might be its greatest strength. Free from bureaucratic red tape, Starshot's team can iterate quickly, embracing high-risk, high-reward approaches traditional agencies avoid. SpaceX's success with reusable rockets proved skeptics wrong by merging Silicon Valley agility with aerospace grit. Starshot's backers point to Moore's law like progress in photonics and materials science, where costs plummet as tech scales up. They envision a future where laser arrays power more than interstellar probes, perhaps clearing orbital debris or beaming energy to lunar bases, making the tech self-sustaining. The ultimate question isn't just whether Starshot can overcome these hurdles, but whether humanity should pour resources into interstellar gambles when urgent problems like climate change demand attention. Critics call it a vanity project for the ultra-wealthy, diverting talent and funds from Earth-bound crises. Supporters frame it as existential insurance, a stepping stone to becoming a multi-planet species before the next asteroid or nuclear winter strikes. Perhaps the truth lies in the middle. Starshot's legacy might not be a fleet at Alpha Centauri, but the innovations born from trying. Lighter sails spun off for solar system exploration, laser networks repurposed for deep space comms, or even just proving that audacious ideas attract the brightest minds. After all, the Apollo program gave us satellite TV and MRI machines while aiming for the moon. Starshot's real achievement could be teaching us how to think and dream at interstellar scales. Buried in the perpetual shadows of the moon's polar craters lies a treasure more valuable than gold: water ice. This isn't just frozen H2O. It's the key to unlocking the solar system, and companies like Intuitive Machines are racing to mine it. Picture a lunar outpost where robotic drills plunge into the darkness, hauling up ice that's been untouched for billions of years. That ice, when split into hydrogen and oxygen, becomes rocket fuel, the same propellant that powers everything from SpaceX's Starship to NASA's deep space habitats. Suddenly, the moon isn't just a destination, it's a cosmic gas station, and the savings are staggering. Launching fuel from Earth costs thousands of dollars per kilogram, but producing it on site could drop that price by 90%, turning Mars missions from budget-busting odysseys into routine commutes. Intuitive Machines, fresh off its historic private moon landing, is betting big on this vision. Their planned Polar Resources ice mining experiment, or Prime 1, aims to be the first demonstration of lunar prospecting, using a drill and mass spectrometer to sniff out and analyze ice deposits near the South Pole. But they're not alone. Competitors like Astrobotic and iSpace are designing their own ice-harvesting rovers, while startups like Lunar Outpost are developing mobile refineries that could roam from crater to crater, processing ice on the go. The business model is simple: sell fuel by the ton to NASA, SpaceX, or anyone else heading deeper into space. The technology is as ingenious as it is demanding. Extracting ice from lunar soil, a mix of dust and permafrost called regolith, requires heating it to release water vapor, then condensing it back into liquid. In the moon's vacuum, even a warm drill bit could cause water molecules to boil off instantly, so systems must be airtight to capture every precious drop. Then there's storage. Liquid hydrogen is notoriously finicky, prone to leaking through metal tanks or evaporating if not kept at cryogenic temperatures. Solutions range from super-insulated containers to converting hydrogen into safer compounds like ammonia, which can be cracked back into fuel when needed. The geopolitical stakes are just as high. The moon's ice is concentrated at the poles, creating a land rush for prime real estate. The Artemis Accords attempt to prevent conflicts by promoting transparency, but with China planning its own lunar base, tensions over resource rights loom. Some propose treating ice deposits like international waters, a shared resource, while private companies push for ownership rights to justify their investments. One thing's certain: whoever controls lunar fuel could dictate the economics of space for decades. Beyond fuel, lunar ice could quench astronauts' thirst, grow hydroponic crops, or even be converted into breathable oxygen. But the grand prize remains propulsion. Imagine a future where ships bound for Mars dock at lunar depots, topping off tanks before slinging into deeper space. The alternative, dragging all that fuel up Earth's gravity well, is like trying to road trip across a continent with a gas tanker chained to your bumper. The challenges are brutal: drilling in -200°C temperatures, operating machinery that must survive weeks of darkness, and scaling operations from lab prototypes to industrial output. Yet the payoff is a paradigm shift, transforming the moon from a scientific curiosity into the hinge point of interplanetary commerce. Every gram of water mined there isn't just a resource, it's a stepping stone to the stars. But lunar fuel depots don't just raise technical questions, they ignite fiery debates over who owns the moon's frozen water. Right now, the Outer Space Treaty of 1967 prohibits nations from claiming celestial territory, but it's silent on corporations mining resources. That legal gray zone has sparked a gold rush mentality, with private companies lobbying for the right to stake de facto claims by planting drills near ice-rich craters. Imagine a scenario where SpaceX fuels its starships using water extracted by a robotic fleet owned by a start-up headquartered in Luxembourg, while China's state-run miners operate just kilometers away under different rules. Without clear frameworks, the moon could become a wild west of competing interests where finders-keepers clashes with international cooperation. Some argue lunar resources should follow the Antarctic model, a commons managed by treaty where science takes priority over profit. Others push for a licensing system where miners pay royalties into a global fund supporting space exploration for all nations. Then there's the darker possibility, a free-for-all where powerful nations and corporations dominate access, leaving smaller players frozen out. The moon's poles are especially contentious because prime ice deposits are concentrated in just a handful of permanently shadowed regions. Control those craters and you control the interplanetary fueling network, a prospect that's already drawing comparisons to 20th century oil geopolitics. Yet the stakes are even higher than fuel. Water is survival in space, not just for propulsion but for drinking, radiation shielding, and growing food. Whoever masters large-scale lunar mining could become the landlord of Earth's orbital economy, charging rent for refueling satellites or resupplying space stations. That's why agencies like NASA are investing in situ resource utilization experiments, aiming to establish best practices before commercial operations scale up. The goal: to prevent a scenario where the moon's resources meant to unite humanity in exploration become another battleground. The clock is ticking. As rockets grow cheaper and robotics more advanced, the first viable lunar mine could be just a decade away. Will we repeat Earth's mistakes, fighting over scraps in the cosmos? Or will the moon become the testing ground for a new era of shared stewardship, where resources unlock the solar system for everyone? The answer might determine whether we're destined to become a spacefaring civilization or remain squabbling in the cradle. Venus isn't just Earth's sister planet, it's a cautionary tale of climate catastrophe turned up to 11. With surface temperatures hot enough to melt lead, crushing atmospheric pressure, and clouds of sulfuric acid, it's the solar system's most inhospitable world. Yet NASA Da Vinci I+ mission is charging straight into this toxic inferno, armed with a probe designed to unravel two of Venus's biggest mysteries. The fleeting whiffs of phosphine gas detected in its clouds, a potential hint of life, and the planet's volcanic secrets, which could explain how a world once possibly habitable became a pressure cooker. The stakes couldn't be higher. Phosphine, a molecule that on Earth is almost exclusively produced by microbes or industrial processes, shouldn't survive long in Venus's acidic atmosphere unless something is continuously replenishing it. Da Vinci I+'s descent sphere, armored like a deep-sea submarine, will plunge through the planet's haze, sniffing the air with precision instruments capable of distinguishing phosphine from false signals. But the mission's true genius lies in its dual focus. As it falls, lasers will map the towering highlands of Alpha Reggio, a region suspected to be volcanic. If active lava flows are spotted, it would prove Venus isn't the geologically dead world we assumed, but a planet still reshaping itself, with eruptions potentially fueling atmospheric chemistry that mimics signs of life. Meanwhile, the European Space Agency's Envision orbiter will approach the puzzle from above. While Da Vinci I+ takes a one-shot dive, Envision will spend years circling Venus, using radar to peer through its opaque clouds and map the surface in unprecedented detail. Think of it as an orbital detective tracing lava channels, measuring ground deformation, and hunting for hotspots that betray active magma chambers. Together, these missions form a tag team. DaVinci Plus delivers the ground truth with atmospheric samples, while Envision builds the big picture of Venus's geologic heartbeat. The contrast in their strategies highlights a fundamental tension in planetary science. DaVinci Plus is a daredevil, a high-risk, high-reward plunge into the unknown, gathering data that can't be obtained any other way but with no do-overs. Envision is the methodical archivist compiling evidence over time to rewrite textbooks, yet both share a goal: to crack the code of Venus's climate apocalypse. By understanding how a planet with Earth-like ingredients became a hellscape, we might just learn how to protect our own world from a similar fate. The implications stretch beyond science. If phosphine hints at aerial life forms floating in Venus's temperate cloud layers, it would redefine the search for extraterrestrial biology, proving life can thrive in the most un-Earth-like places. And if volcanoes are indeed churning beneath the clouds, it raises a tantalizing possibility that Venus, not Mars, could be the solar system's next frontier for human exploration, with floating cloud cities harvesting sulfuric acid for resources and studying extremophiles in situ. DaVinci Plus and Envision aren't just missions, they're time machines. By decoding Venus's past, they could reveal the future of habitable worlds, including our own. And hidden in their data might be the answer to whether life is a cosmic fluke or a universal inevitability, waiting to be found even in the most unforgiving corners of space. Venus stands as a stark monument to what happens when a planet's climate spirals out of control, a runaway greenhouse effect so extreme it turned a world once possibly lush into a scorching wasteland. Scientists believe Venus may have started as a twin to Earth with oceans and temperate climates until a cataclysmic cascade of feedback loops sent its temperatures soaring. The same carbon dioxide that exists harmlessly in Earth's atmosphere now blankets Venus at 90 times our pressure, trapping heat so efficiently that surface temperatures reach 470 degrees Celsius. That's hotter than a pizza oven, sustained not for minutes but for billions of years. The terrifying lesson: Earth is flirting with the same forces, just on a slower timeline. The parallels are impossible to ignore. On Earth, human activity has pumped atmospheric carbon dioxide levels to their highest point in 3 million years, still a fraction of Venus's crushing blanket, but rising at an unprecedented rate. Venus's past tipping points, perhaps triggered by volcanic eruptions that belched enough CO2 to overwhelm natural buffers, show us how delicate the balance really is. Once certain thresholds are crossed, the planet's climate systems can flip into a self-perpetuating furnace. Water vapor, a potent greenhouse gas, evaporates from warming oceans, trapping more heat and evaporating even more water in a vicious cycle. On Venus, this process ran until the oceans boiled dry, leaving behind a desiccated wasteland. Earth's oceans aren't at risk of boiling away anytime soon, but the mechanism is identical in kind, if not yet in scale. Here's where Venus's nightmare becomes our warning. Studies of its atmosphere reveal how sulfuric acid clouds, born from evaporated water and volcanic sulfur, now reflect sunlight so effectively that Venus absorbs less solar energy than Earth, yet its surface is far hotter. The reason: its thick CO2 atmosphere doesn't let infrared radiation escape. On Earth, we're seeing a milder version of this trap. Melting ice caps reduce reflectivity, darkening surfaces to absorb more heat. Thawing permafrost releases methane, a greenhouse gas 30 times more potent than CO2 over a century. These feedback loops are the same demons that doomed Venus, just moving at a pace that still gives us a slim window to intervene. Yet Venus's tragedy also holds a sliver of hope. By studying how its atmosphere traps heat, scientists refine climate models for Earth, plugging gaps in our understanding of cloud dynamics and gas interactions. Data from Da Vinci Plus could reveal exactly how Venus's water vanished, whether it was stripped by solar winds or chemically bonded into rocks, helping us predict which of Earth's stabilizing systems might collapse next. There's even a macabre optimism in Venus's extremes. Its conditions are so hostile they've become a testing ground for materials and technologies that might one day shield Earth from overheating, from ultra-reflective atmospheric aerosols to carbon-scrubbing synthetic enzymes. The takeaway isn't that Earth will become Venus tomorrow. It's that planetary climates aren't static, they're dynamic systems with tipping points. Venus shows us where the road ends if we ignore the signs. But it also proves that atmospheres obey physical laws we can measure, predict, and potentially re-engineer. The difference between a habitable Earth and a sterile Venus isn't fate. It's the choices we make while we still have time to change the trajectory. Deep in the asteroid belt between Mars and Jupiter floats a world unlike any other, not a chunk of rock or ice, but a gleaming metallic relic that might hold the key to understanding our own planet's violent birth. Asteroid 16 Psyche is a cosmic oddball, a 200-kilometer-wide nugget of almost pure iron and nickel that glints in the sunlight like a forgotten treasure. This isn't just another space rock. Scientists suspect it's the exposed, frozen heart of a failed planet, a protoplanet whose outer layers were blasted away in the solar system's chaotic early days. If they're right, Psyche offers something we can never reach on Earth, a direct look at the hidden core that shapes our world's magnetic field, drives plate tectonics, and protects life from deadly solar radiation. NASA's Psyche mission, launching in 2023, is humanity's first visit to a metal world, a journey that could rewrite planetary science. The spacecraft, armed with a gamma-ray spectrometer and a magnetometer, will orbit Psyche for 2 years, mapping its composition and magnetic field in exquisite detail. What it finds might settle a heated debate. Is Psyche truly the corpse of a protoplanet's core, or something even stranger? Some theories suggest it could be the remnant of a rare iron-rich asteroid that formed near the Sun before being flung outward, while others propose it's the product of unimaginable cosmic collisions that stripped away its rocky shell, leaving only the metallic guts behind. The implications are staggering. Earth's core, buried under thousands of kilometers of rock, remains as inaccessible to us as the far side of the galaxy. Temperatures there surpass 5,000 degrees Celsius, and pressures crush matter into exotic states we can only simulate in labs. Psyche, if it is indeed a naked core, gives us a time capsule from that inferno, frozen in the vacuum of space. By studying its structure, we might finally understand how our own planet's dynamo generates its protective magnetic shield, or why Mars lost its field and became a barren wasteland. But Psyche isn't just a scientific curiosity, it's a potential goldmine in the literal sense. The asteroid's metal content, iron, nickel, and possibly rare elements like platinum and gold, has sparked dreams of asteroid mining. Estimates suggest its resources could be worth quadrillions of dollars if hauled back to Earth, though the real value lies in using them in space. Imagine refineries on Psyche, processing its metal into construction materials for orbiting space stations or fueling depots for Mars-bound ships. The mission will test the viability of such schemes, analyzing how metals behave in microgravity and whether they could be mined with future robots. Yet the greatest treasure Psyche offers might be philosophical. This mission forces us to confront how little we truly know about the building blocks of planets, including our own. Every crater on Psyche's metallic surface could tell a story of ancient collisions that shaped the solar system, while its magnetic whispers might reveal how planetary cores live, die, and perhaps even reboot. As the Psyche spacecraft closes in on its target, it carries more than instruments, it carries a mirror. By studying this alien core, we're glimpsing the hidden engine of our own world, the molten heart that keeps Earth alive. And tucked in its data might be answers to questions we haven't even thought to ask. How common are metal worlds? Could they host magnetic fields that protect life? Or are we the fluke, a rocky planet that somehow kept its core buried and its oceans full? Psyche doesn't just hold the secrets of the past, it might hold clues to our future among the stars. Psyche's metallic composition isn't just a scientific curiosity, it's a potential economic game-changer on a scale that defies earthly markets. Initial spectroscopic readings suggest the asteroid contains staggering quantities of iron, nickel, and possibly platinum group metals like rhodium and palladium, all forged in the violent collisions of the early solar system. Crunch the numbers, and the raw material value could exceed $10,000 quadrillion, enough to theoretically make every person on Earth a billionaire overnight. But here's the catch. Flooding terrestrial markets with that much metal would instantly crater global commodities, rendering gold as worthless as gravel and destabilizing entire national economies built on resource extraction. The real fortune lies not in bringing these metals home, but in using them as the foundation of an off-world industrial revolution. Picture robotic factories on Psyche itself, smelting its iron into girders for orbital megastructures, or printing nickel alloy components for Mars habitats without the absurd cost of launching every nut and bolt from Earth's gravity well. Yet the legal framework for claiming these cosmic riches remains murkier than Psyche's shadowed craters. The 1967 Outer Space Treaty bans nations from claiming celestial bodies, but says nothing about corporations strip mining them. Startups like Astroforge and Planetary Resources argue that asteroid resources should follow maritime salvage laws, finders keepers, while the United Nations proposes treating them like deep-sea minerals, managed collectively for humanity's benefit. The tension boils down to a philosophical clash. Is space the new frontier, ripe for private enterprise, or a commons to be preserved? Recent precedents lean toward privatization. In 2015, the U.S. passed the Commercial Space Launch Competitiveness Act, granting U.S. companies ownership of whatever they extract from asteroids. Luxembourg followed suit, creating a legal haven for space mining ventures. But with China drafting similar laws, the stage is set for a Wild West scenario where whoever plants a drill first could de facto claim entire worlds. The ethical dilemmas run even deeper. Psyche's metals were forged in protoplanetary collisions over 4 billion years ago, irreplaceable artifacts of our solar system's birth. Should we treat such places as mines or museums? Some planetary scientists warn that unbounded mining could erase cosmic history before we've even decoded it, like melting Inca gold into ingots without studying the artifacts. Others counter that humanity's survival may depend on accessing space resources to avoid exhausting Earth's dwindling reserves. There's also the environmental paradox. Exploiting asteroids could spare terrestrial ecosystems from destructive mining, yet risk littering orbit with refinery debris that jeopardizes satellites and future missions. Perhaps the most radical solution is to leave Psyche's metals untouched for now. Instead of strip mining, we might send autonomous labs to study its composition in situ, unlocking metallurgical secrets that could revolutionize recycling on Earth. Or we could treat it as a cosmic backup drive, preserving its resources until the day we develop technology to use them sustainably. One thing's certain, the decisions we make about Psyche won't just shape space economics, they'll define what kind of interstellar civilization we aspire to become. Will we repeat Earth cycles of resource wars and environmental exploitation, or forge a new model where abundance doesn't have to mean destruction? The answers may lie buried in Psyche's silvered craters, waiting for us to dig responsibly. Forget blurry dots and educated guesses. Imagine seeing an alien Earth floating in the void, its blue oceans and swirling weather patterns crisper than a high-definition postcard. That's the promise of the Habitable Exoplanet Observatory, or HAB-X, a next-generation space telescope designed to do what no instrument has managed before: directly photograph Earth-like worlds orbiting distant stars and scan their atmospheres for the chemical fingerprints of life. Unlike missions that infer planets through shadows or gravitational wobbles, HAB-X will capture actual images of these worlds, separating their faint light from the blinding glare of their parent stars with a piece of engineering so elegant it borders on sci-fi, a massive, flower-shaped starshade flying 40,000 kilometers ahead of the telescope like a cosmic parasol. This starshade isn't just a fancy sunshade. It's a precision instrument with petals meticulously designed to diffract starlight outward, canceling it out so the telescope can spot planets a billion times dimmer. Picture trying to see a firefly hovering next to a searchlight from miles away. That's the challenge HAB-X overcomes. The payoff, a catalogue of dozens of Earth 2.0 candidates, each analyzed for atmospheric gases like oxygen, methane, and water vapor. But HAB-X goes further. Its ultra-sensitive spectrographs could detect industrial pollutants like chlorofluorocarbons or even artificial illumination, subtle hints that we're not the only civilization to tame fire and invent the light bulb. The telescope's targets read like a roll call of cosmic real estate. Proxima Centauri b, a potentially temperate world just 4 light-years away, tops the list, but HAB-X will also scour systems like TRAPPIST-1, with its 7 rocky planets, or enigmatic red dwarfs where life might cling to tidally locked twilight zones. Each candidate will be scrutinized for bioclues, unusual molecular combinations that don't last unless replenished by biology. Oxygen and methane, for instance, rapidly destroy each other unless something keeps producing them, as life does on Earth. Yet HAB-X's ambitions stretch beyond mere detection. By studying the diversity of exo-Earths, some richer in water, others with thicker atmospheres or unusual axial tilts, it could reveal how common our planet's delicate balance really is. Does Earth sit in a Goldilocks zone for complex life, or is it just one flavor in a cosmic buffet of habitable worlds? The answer could redefine everything from astrobiology to our place in the universe. The technological hurdles are as daunting as the rewards. The starshade must deploy flawlessly in deep space, maintaining perfect alignment with HAB-X despite solar winds and micrometeoroid nudges. Meanwhile, the telescope's mirrors need polishing to atomic-scale smoothness to avoid scattering light that could drown out planetary signals. And with a projected price tag rivaling James Webb's, securing funding will require convincing skeptics that finding another pale blue dot is worth billions. But if HAB-X succeeds, its legacy won't just be scientific, it'll be existential. A single image of a living world beyond our solar system would answer humanity's oldest question: are we alone? And tucked in the data might be an even profounder revelation: that life isn't just a miracle but a cosmic imperative, blooming wherever the universe gets half a chance. For every exoplanet that checks the boxes for habitability, right size, right temperature, right distance from its star, there's a brutal cosmic caveat: the universe loves building traps. Take Kepler 438b, a world once hailed as Earth's near twin, orbiting comfortably in its star's habitable zone. Then astronomers discovered its sun unleashes apocalyptic flares every few months, sterilizing the surface with radiation. Or consider Kepler 22b, a promising ocean world until follow-up studies revealed its atmosphere was likely stripped away eons ago, leaving behind an airless rock. The galaxy is littered with these false hopes, planets that look perfect until closer inspection shows their deadly flaws. Yet for every Kepler 438b, there's a surprise like Kepler 442b, a planet soaking in just enough sunlight to host liquid water with a stable orbit around a calm star. Even more intriguing are the superhabitables, worlds slightly larger and warmer than Earth, where higher gravity might foster thicker atmospheres and shallower oceans, creating ideal conditions for biodiversity. Recent analyses of Kepler data suggest these planets could be more common than Earth-likes, raising a tantalizing possibility: what if we're the odd ones? The debate boils down to two competing narratives. Pessimists point to the Great Filter theory, the idea that some invisible hurdle, like rampant climate instability or the rarity of complex life, prevents most habitable planets from evolving intelligence. They note that even on Earth, life stayed microbial for 3 billion years before multicellular organisms took off. Optimists counter with abiogenesis momentum, the notion that once life sparks, it tends to diversify quickly, filling every niche. Mars may have been habitable once. Europa and Enceladus could host life today. If life emerges easily but gets snuffed out by cosmic disasters, the galaxy might be a graveyard of biospheres that never had time to flourish. The wild card water worlds. Kepler found dozens of planets 2 to 4 times Earth size with densities suggesting they're mostly H2O, not covered in oceans but made of them with no land in sight. Some astrobiologists argue these could be aquatic paradises where marine life thrives in global, tideless seas. Others warn they'd be nutrient deserts lacking the mineral cycling continents provide. Without clays or volcanic vents to concentrate organic molecules, life might struggle to advance beyond pond scum. The biggest Kepler revelation, though, is sheer numbers. Statistically, every star in the Milky Way hosts at least one planet, with billions sitting in habitable zones. Even if only 1% of those hit the life jackpot, that's still millions of worlds. The catch: distance. Our nearest exoplanet neighbor, Proxima Centauri b, is 4 light-years away, close enough to tantalize, too far to confirm without missions like HAB-X. Until then, the great alien Earth debate remains just that, a debate. But with every new telescope and dataset, the pendulum swings between two equally profound answers, that we're either utterly ordinary or terrifyingly alone. From hunting for alien biosignatures to mining the solar system's resources, these 25 missions represent more than just scientific ambition. They're humanity's collective bet on our future among the stars. Each one carries the potential to crack open cosmic mysteries that have haunted us for centuries. Are we alone? The James Webb Telescope and HAB-X might finally spot the chemical whispers of life on distant exoplanets, while Europa Clipper and Da Vinci Plus could uncover organisms thriving in the unlikeliest corners of our own solar system. Can we survive beyond Earth? Artemis and lunar mining ventures are laying the groundwork for interplanetary colonies, while breakthrough starshot tests whether the stars themselves are within reach. But the real magic lies in how these missions intertwine. Psyche's metallic heart could teach us how to build spacecraft that last millennia, while Rubin Observatory's sky scans might pinpoint our next destination or warn us of threats barreling toward Earth. Even failures would be revelations, proving which paths are dead ends and which demand a second look. Together, they sketch a roadmap for becoming a multi-world species, one where the Moon is a pit stop, Mars a stepping stone, and the cosmos no longer a frontier but a home. This isn't just about rockets and data. It's about rewriting what it means to be human in a universe vaster than our ancestors dared dream. Every image of an alien sunset, every gram of water extracted from lunar soil, every signal from a probe sailing toward Alpha Centauri pushes the Overton window of possibility. The questions these missions answer or raise will echo through textbooks, policy debates, and bedtime stories for generations. So now it's your turn. Which mission sets your imagination ablaze? The telescope that might snap a photo of another Earth, or the drone destined to soar through Titan's methane skies? The robotic geologist cracking open Mars secrets, or the nanocraft racing toward the stars? Drop your pick in the comments and let's geek out about the golden age of exploration unfolding right above our heads. The cosmos isn't just waiting to be discovered, it's waiting to be claimed, and the next chapter starts